start recording on this computer as well. So okay. Uh so I graded like your homework, but I didn't have time to look at your uh project proposal yet. So but I will look into that like later this week. So and I have some echo. I need to turn that for. So yeah, about the homework, like so a couple of things like you have to make sure that I guess uh you see like sometimes I deduct some of you guys like points like uh mostly is like when actually you mm, the most deduction you will get is like when you have something is apparently not working. So um just think of like I take the grading is more or less like in a real world situation, right? If you have submission, like finish your work, like submit to your boss, and then like if that thing is apparently doesn't work, for example, like I it's supposed to detect blue, and then like it just like apparently there's a blue there, somewhere blue there, but it's not detecting. Then right away you know if something is wrong, right? So that is expected to be catch to be caught. If it's not, then like you definitely will get like kind of like half of the point deducted, half the points deducted. And same situation actually like I guess for also homework to here I guess I in the past I give this similar assignment like for people to generate composting images, and they kind of like give a result like this, like not all of them, like some of them. So apparently this is wrong way. So if you just simply put two images together, if you see it, you know that right away is wrong way. So I will give like credits for effort, but you expect we only get half of the points basically. So and that's basic. And also like one thing I have like a small deduction for you guys to have like hard coding. So in your code and more precisely, I did a point like when you guys say just put the, for example, the image size directly into the code because like that is very bug prone, prone. I don't know how to pronounce that because like if you think of like you just like plug in your, I mean plug in another like webcam or like you move your code to another computer, it right away will crash. So for stuffs like that, like I will give a minor deduction for that. Just have you guys remind that like you shouldn't do that because um sometimes it's acceptable. Like for example, like number of channels you expect it's not going to change. You put three there, it's kind of okay. It seems like even silly if you just define number of channel all the time. But for many cases, like the size of the image, like you expect it will vary, like whenever you put in a different file or something. Then if you hard code that, then definitely you will crash at some point. Yeah. So and that's basically it about the homework and so on. So okay, if there's no particular question, I guess I'll move on to talk about what I like to talk about today. I was thinking to talk about uh kind of like because we talked about edge detection last time, it seems like okay, natural to talk about corner detection this time. But I think that maybe I should talk about image warping first because like when I talk about Harris corner detection, it involves a little bit kind of understanding of like the image warping. But this is not something new. I guess I maybe some of you is new, some of you may not, but uh, we kind of like briefly mentioned that like when we talk about Fourier transform, like the projection and so on, but very briefly. So but okay, just think of like I give a couple motivation slides and then I maybe just I mean use handwriting uh derivation and probably like more easy to digest. So okay, uh first some motivation. First I have like trying to do image alignment, right? Let's say I have two images. I don't have two images, but let's say this is two images. Let's see if I have one, no, I don't have that yet. So I actually have two images. I want to merge them together. So do an alignment. So if if, no matter how good I'm aligning them, if I don't first warp these two images, I won't get a good result. So if you want to create mosaic, like definitely you need to do image warping. And I'm also maybe you want to have like an object like appear in two different scenes, and you want to see how they're related. And in this case, you probably want to do a warping to maybe this one, rotate and rescale to this one, and then I find here. And so like the yeah, that's the two photos at the beginning. So if I'm able to warp this image first, these two photos first, I can align them very well. So okay, basically what we are going to talk about that today. So um I guess okay, maybe I just depends on, because you guys have really varying background. I guess I'll start with something really simple, just say trigonometry, that maybe you remember or forgot, or remember or okay, remember or forgot. Yeah, that's okay. Remember or forgot. So let's say I have, okay, just a simple question here. Let's say here is let's say this line here is length 2, and I have a theta here. And what's of the length of this length here? Let's say L. What's the length here? This is a question. Okay, very good. But the problem is like, okay, so yes, I have like 4, 5. Yes. I have a couple of them. So okay, uh, I have like almost some sine or some cosine and so on. Yeah, the form is right. Yeah, but yes. Okay, now it's converging to the correct solution. I guess yes. So this is two sine theta, right? In general, if this is R, let's say, then this will be like R sine theta. So on the other hand, this one will be cosine theta or R cosine theta, right? So just simple trigonometry here, right? So now okay, now let's start with rotation, right? We want to do warping, right? So let's say I have image here. Now I warp it, or in the sense I just rotate it. Let's see. I guess some of it. Yeah. Okay. You managed to mirror it. Okay, that's fine. So if I rotate, let's say rotate this one by uh theta degree, let's say, right? Then it becomes something like that, right? So now we want to, okay, we first consider what's rotation, or like what's warping, like in general. So what we are doing here is like I have an initial image. I say I can consider as a function, right, or like intensity. I mean the intensity over the pixel is like like a function, right? So I can have like this image fxy here. So basically saying that like fxy is like for a particular, okay, let's use just the Euclidean coordinate that we are familiar with instead of like what user computer use. So let's say this is x-axis, this y-axis, right? So let's say I have like some point here, let's say just this point here, let's say if it's just 1, 0, let's say, then this I have some intensity here, right? That's I have is basically f1, 0 here. Now, when I rotate this image, it means that like I have this new location should be equal to this point, right? So I have the new rotated image, let's say it's like gxy here. So I should have this point here, I don't know what is that. Let's say is xy or something like. Maybe I put it another notation x0 x0 y0. Let's say, so I should have like gx0 y0 is equal to f10, right? Something like that. Right? So you agree with me for that? So basically, as you can see, like a rotation or like in general, image warping is basically like you have a transform of your coordinate. So I have like start with, let's say in general, like I have fxy here. It will map to some new coordinate. So I have, let's say I have some transform here, t, that for this one here is like from 10 is mapped to like x0, y0. So in general, I have this transform, like let's say xy is going to map to like tx0, oh sorry, txy here. So therefore, like I basically I have this like gxy, or like I should say gt, x, this is a, maybe I write like that, tx, ty, xy. It's a little bit tedious, but maybe I just write a vector form here. Like let's say x is mapped to like t x here. So this is also a vector here. So that vector in the sense I have two coordinates here, right? Originally you have two coordinates. So you mapping like have this t here, this transform here mapped to like also like two coordinates tx. The first, I mean, have like basically two coordinates, basically like this. Yeah, okay. So, and I will have gtx is equal to fx, something like that. So basically, so okay. I hope I'm not confusing you. So it's just what I want to emphasize here is just that like you see like I'm basically transforming the coordinates here, right? So I have the original image. I transform the coordinate um, to get the new image. Uh, of course, I can also write in terms of like actually creating the image. I will basically doing something like that, right? I have the new image I want to generate, right? So if I want to know what is the x for this, I mean the intensity at the point x here, I should just do an inverse of this one, right? So I will inverse this and then go back to look at like what's the intensity of the inverse t of that coordinate, right? So okay. So of course, if you have the image is discretized, that's basically always the case. Then in general, this one uh, will not be equal to an integer. Right? So we will not be have integer coordinates, right? Maybe I will get back here. So let's say I have this is uh, I want to look at what's the pixel at 5 and 4, let's say. Then I do an inverse transform of t here. I get back like 6.5 and 7, let's say. Now for this one, I don't have like 6.5 and 7 for f here, right? But what we do is we can do interpolation as what we did last time, right? So I can, this one, I can approximate this as, let's say f6, 7 plus f 7, 7, and then I take the average of them, something like that. So, okay. So this is just a general in generic like uh, image warping. And one thing like note that like here like when I do warping, I'm transforming the coordinate, right? So on the other hand, like, if you think of filtering, I'm actually transforming the intensity instead. So let's say if I have the image fx here, original image, when I do filtering, I actually applying the filter or like modifying the intensity of that one, right? So, or like I have a filter image, let's say G here, Gx is actually equal to, I have a, let's say I filter H here is equal to HFX, something like that. So, so this is filtering. this is warping. Warping will be like gx will be, I apply the transform, let's say here, tx here, at the coordinate itself. Yeah. T or T inverse, it doesn't matter. Yeah. So, okay. Now, but let's go back. Okay, here I can't elaborate. I just want to kind of like explain this stuff. So therefore, like yeah, also like give a more general case in general for warping. But let's go back to something more specific. Let's say go back to rotation here. So let's see. Let me just erase all this. Ah. Oh. So I will take. Okay, let's just consider a simple case now here, exactly here, right? So I have like 1 0. Now I mean like this coordinate here, like for the new image g x0 y0 should map to this one. Let's say this, I mean let's say I would, as I just said, like I have this image, I rotate by theta degree. Now let's give a question here. So question is like, where is this point here that correspond to this point like 1 0 here? So that's basically what is x0 y0 such that gx0 y0 is equal to f10. So where g is basically is an image rotated by theta degree of this one. So this is like rotate by theta degree. So what will be the coordinate here? Rotate up like here. Rotate counterclockwise. Yeah, we just do the convention that like typically the convention in geometry is like theta when it's positive is like counterclockwise. I mean when clockwise is like negative. Yeah. Okay. Yes. Couple more. Yes, actually, if you know this, it should be easy, right? You have this one here. You rotate it, you look at this, right? This, well, if you rotate it by theta degree here, now this is 1 0, right? So therefore, like this length here is 1, right? So therefore, like, I have 1 here, right? So then the new point here, basically, let me draw also like that, the image here. So this length is 1 here. So then the coordinate here is basically along this x-axis is like the length here, right? The length here, you know, is cosine theta, right? And along this y-axis is sine theta, right? So therefore, the coordinate here, coordinate here will be just cosine theta and sine theta, right? So okay, let's do another questions in a similar manner. So let's say if I have, instead of this point here, now the origin is this point. Now look at this point here, this corner here. So this point, when it mapped to like this point here, so where is this point here? So that is basically, let's say I call it x1, y1, let's say such that g x1, y1 is equal to f c1, let's say. You may want to put a Q fee when you answer that, like because like that's a or fee like that's a I guess these two questions are kind of close. Uh, so what is what will be this one? Like, oh, okay. I'm sorry. Actually, I didn't pay attention. Are you guys all finished with the second one? You guys are okay with the explanation for the second one? I think yeah, I got most of the answer here. Should be fine. Yes, I cannot. Yeah. Oh, okay. Q. The third question is now instead of like the second question is say looking at this point, right? Where's this point, right, in the new image? Now it's looking at like where's the new point for this in the new image here. So that's basically this corner like uh CO1, right? So this corner, let's say is CO1. So where is CO1 in the new image? So so that map to, let's say, this x1 y1 here. So that this x1 y1. So where's this x1 y1? This corner that map to this original like uh, upper left corner there. So anyone else? Like uh, so okay. Logan, I don't think like that cosine theta sine theta is that the answer for question 2 or question 3. So it should not be the same for yes, yes. We I'm oh, okay, yeah, that's fine. Yeah. Okay, I guess many of you get it. Yeah, actually, yes, you can just think of like a pi over 2 here, right? Because I now I basically it's like you rotate, it's like you starting from here and rotate by you can use the same solution as like previously, but you are like rotating like theta and then rotate like pi over 2 again, then you get basically this will be, or actually you can look at it by observation also, like so in this case like the theta is here, right? Theta is here. Now what's the coordinate here? Apparently it's like going back like in the x coordinate is minus something, right? Minus the length of this way, minus length of this is minus sine theta, and then like and the height is along the y-axis will be positive, right? Will be the positive length of this will be like just cosine theta, right? So therefore, like I will have, oh, this is very difficult to read. I know. Uh, Let me, yeah. So what I mean is like if I just start from here, I rotate by theta, right? So then it will be, this is again 1 here. Then this coordinate will be along the x-axis is minus the length of this is basically minus sine theta, right? So this is sine theta, and the height will be like cosine theta, right? So therefore the coordinate it would be like minus sine theta cosine theta. Right? So uh, so if you guys are all good with that, let's start with the final question here. So I guess so in general, what will be the points and if I have this image now I have any particular point xy here, right? Now rotated by theta degree. Now this is a new point, let's say this time maybe call it x x tilde y tilde, let's say. So I have like start with what is x tilde y tilde basically, such that like in general now gx y is equal to sorry gx tilde y tilde is equal to fxy, let's say. So anyone, my question is clear. So oh okay. The question is now go to the general case. Like if I have or maybe like okay maybe I just make it like it doesn't necessary. Let's say just like how about 1 and 2, let's say. Similar question. Now it's like we try the corners, right? So now in general, let's say maybe not 1 and 2, maybe 2 and 3, let's say. So same question now, but not the points along the axis, but like now some point like at the coordinate 2 and 3, how this point like at 2 and original coordinate at 2 and 3 will be mapped to the new coordinate in the new, I mean the coordinate, the new image. So basically, what will be the new coordinate there? Yes, someone had the solution. Yes. Okay. Actually, my point here probably is not this location. Let me we put the point to make it more realistic. Let's see. 2 and 3 maybe is somewhere here. Let's say, yeah. Me. So this point here. Yes, I guess most of you got that. So the way you think of that is just a linear combination, right? So uh, you know where it mapped to, let's say, 2M0, because I know where it's mapped to, like 1M0, right? Mapped to 2M0 will be just, what's that again? Like it's 2 cosine theta and 2 sine theta, right? So this point will map to 2M0. And then to map to map to uh, 0 and 3, that point will be like minus, is that minus? Yeah, minus 3 sine theta. And 3 cosine theta. So then, like, if you think of like, so I know what's the point for this guy. This is like 2M0, and this is like 0 and 3. Basically, this point will be like linear combination of that, right? So I will be like this at this will be the same as, okay, the point is here. So I know okay, basically I know this coordinate and I know this coordinate. So it will be just like this one at this one, like vector addition, and you will get like this point here. So therefore, like, okay, then we can write in general, like what's rotation, like to get the rotation. So if I have like, let's say X and Y coordinate, right, start with X and Y coordinate, if I image rotated by theta degree, that for the new coordinate will be something like cosine theta. Okay, the new coordinate will be what? New coordinate will be uh, will map to something like x cosine theta y yeah y sine theta, right? And then like this, and then the y. Okay, am I right? Count for right? I don't know. Wait a sec. X. I guess I better look at your solution. Okay, maybe. Sorry, yeah, sorry, it should be minus sine theta. Yeah, yes. And then this, and the y coordinate is x sine theta plus y cosine theta. Right, the new coordinate. Okay, I'm writing it this way, like that. Yeah, something like that. So, or I can write in a matrix form, it will be like x and y. It will be like cosine theta minus sine theta and like sine theta cosine theta. So this will give me the new coordinate x pi and y pi. So so uh so all of you following what I just wrote. So it's like if I start with like the original coordinate here. Now if I I want to get the new coordinate, we just multiply by this matrix basically. Uh Yeah, I always got confused with that. Well, let's verify that. Like I always worry about this minus sign also. Yeah, I sometimes will. So let's see if it makes sense. So actually the best way to figure out this kind of sign is just like give a simple uh example to see if it works. So okay, if I have like the original coordinate is 1, 0, what should I get? I should get the new coordinate. What I get is this multiplied by this one, right? So I should get this multiplied by this will be equal to cosine theta and sine theta, right? So it looks correct, right? So if I have let's say 0, 1 here, as we showed earlier, 0, 1 should get 0, 1 multiplied by this matrix should be equal to minus sine theta and cosine theta, right? So it seems okay, right? You you are fine with that. So okay. By the way, like for you guys are trying to multiply matrices, uh, when you multiply, like let's say this matrix by 1, 0, or like okay by 1, 0, I guess when you first learn that, like you will try to or like multiply by xy here. The first learn that is like will be like this one multiplied by x, and then this one multiplied by y, right? I'm going to get this value here, and also like for this value will be this one multiplied by x, and this one multiplied by y here. Uh, and actually more conveniently, like usually you can think of this as just also a vector of vector. So you can think of like this one is actually this block here multiplied by x plus this block here multiplied by y. So therefore, when I look at this here, immediately like multiply 1 0 is basically this block multiplied by 1, that's cosine theta sine theta, and this block multiplied by 0, that's nothing. Yeah. So okay. Anyway, so okay, this is rotation. How about scaling? So if I want to scale up and scale down, like or like whatever. So if I want to scale the image by 2, let's say factor of 2. So of course, like this will be pretty obvious, right? So I will have the x pi y pi will be just equal to 2x 2y, right? So that's wait, actually I mix this up. If I expand by 2, then probably say 1/2 and 1/2. Uh, is that right? No. Actually, 2 is right. 2 is right. 2 is right. Right. Then the new coordinate is say 2x and 2y. Right? If I want to scale it, can write into the matrix form? Do you think like you can write in matrix form as a question? So if I want to scale this by 2 times, you see what I mean? Like, can I also have x pi y pi multiplied by some matrix here? Yeah, let's call it t here. Maybe not good idea. Call it t. Just maybe a scaling matrix. I call it. I just m is okay. Like x y. So what will be m here? Or like you can see that what I'm doing is I just what will be the m such that like 2x such that like m multiplied by xy is equal to 2x 2y. Okay, yeah. So uh some got it right. Okay, just one. Yes. So okay. So so anyone who doesn't get it right, like this is important. Like this is very basic. So you 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 can get the solution slowly, but well, I mean you need to understand where it comes from because it is so basically appear in everywhere, like in engineering and computer science and so on. Because this is if you understand like how to play with matrix, you are able to get this way. So and yeah, yeah, the answer would be just 202 right? So if I x, y, I multiply by this. So as I said, like, I can think of like is this one multiplied by x plus this one multiplied by y, right? So therefore it's like 2x 0 plus 0 2y. So therefore we'll get like 2x 2y here. So that's scaling, and you can scale different version, right? So I mean scale not different version along different direction have different scaling. So for example, I can have like in the y direction, maybe I scale 3 times instead of 2 times. Then I will have this one will be replaced by 2 feet, let's say. So I have rotation, right? Rotation and scaling here. So let's also do translation. So for translation, it's again like very simple, right? If I have, let's say, translate by delta x delta y. So if I have the original coordinate, say xy here, let's say my final x pi y pi in this case will be just xy plus this tx delta x delta y, right? So this is super simple. Okay, can I do that? This would be a yes no question now. Can I write x pi y pi equal to some matrix multiplied by xy here? If so, what will be m here? Okay, some say yes, uh, some say no, actually. So for those who say yes, you should also think of like what would be that things, right? So you can put in some actual number, right? So let's say uh, actually those you say no, I guess the easier to verify that is I think of like do I have some uh special case that I can prove that is not true, right? So can I say, for example, like uh let's say think of like any special some special case. So that would be like counter example, where I will prove basically the thing is like when you say yes or no, you should like then like the next question will be like, okay, can I show that? Like if it's yes, will be like what will be my m, right? What will be my m? If it's no, then like can I think of some counter example that like I'm not able to do that? So that there are many more yes. Okay. Uh it's a question good to ask because like when you kind of like go through the materials like so many times you feel like yeah of course something like that, but then like yeah you forgot like actually the first time you read this like it's not actually obvious maybe. So the answer actually is no. And you you uh, you actually you can very easy to kind of like see that why is no because I think of like simple kind of counter example, right? Let's say xy is equal to 0 0. So I'm not say let's say my delta x is just simply 1 1, let's say, right? So now no matter what m I put in, I cannot get that, right? Because I have 1 1 here, I have 0 0 on this side, right? So whatever matrix I put in, multiply this guy will get me 0 0, right? So there's no way I can do that. So okay, it's good. Like I have rotation and sorry, this is even I cannot read the handwriting here. Scaling, rotation and scaling, I can just do a matrix multiplication, right? But translation, I cannot do that. So, but we want to put everything into like multiplication like this. That would be very nice because if I can do that, I can have basically for all the transform, it will be just like let's say I do a rotation and multiply by some matrix MR, and I want to do scaling multiply by another matrix MS, and then I do translation multiply by another matrix MT, let's say. Um, so we want to be able to do that, but we cannot do that like with the Euclidean coordinate. No, it will not work because as I said, like you can just put in a counter example, right? So let's say if I have okay, someone have a question. How about if I try one dx over y and like dy over x and one something like that, right? So but let's say if I have my x and y is equal to 0, okay, I mess up already. Yeah, um, I won't be able to get basically from let's say if I want to translate from like 0 0 to 1 1 here. Oh, yes. So And you're good with that. So basically, oh actually, I guess I can think of other counter example as well, but I guess 0, 0 is easiest to see that. Uh, if you have like the original location is actually 0, 0. So okay, let's see. So but as I said, like, we want to have this kind of like everything as a matrix multiplication, right? So what? No, 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 no. You no, it's not a trivial case. What do you mean by trivial case? Actually, uh if you cannot even handle that point as 0, 0, then it's a major issue for your things, right? No, 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 no. X, Y is arbitrary values, right? Right? X and Y should be up because you have the image, you start with an image, right? You need to be able to map all the points inside the image, right? So that can contain a point, let's say 0, 0 here. So need to know like where's this 0, 0. It would be translated to. So or actually let's just do it like anyway. So like I have X, Y here. So what I get is like uh yeah, actually, what you get is pretty nice. Though. I have to admit that you have like x here plus dx here, and yeah, that's why. Yeah, actually, you make it pretty nice. I'm actually happy with your insights here, but yeah, you actually did pretty nicely. This one actually is true, but the problem wait,
Dr. Chang,
yes.
I'm sorry, I did a mistake. So could you forget about this, Mike?
Oh, okay.
So I just realized that for the translation, it can be also represented by the matrix M using the differentiation derivative. So this matrix
You
1
mean
dx
is
over
that this
y,
one? Is that this one that?
but that is not correct expression. So instead, the diagonal elements are 1, 1 is okay, but off diagonal elements must be delta x times d over dx. And then for the right lower corner, the lower corner must be delta y d over dy.
Oh, okay. Yeah, I'm sorry about that. Actually, I need to say like this is wrong. Actually, I wasn't paying attention myself. Also, like, okay, why this is a problem? Because your M here should not depend on x and y, right? This is the transform itself cannot depend on x and y here. This should be you are kind of like I should say a little bit yeah, in terms of here, it's like kind of cheating because this we want to have this matrix is independent of your data here, right? So if this is depend on the data, then you of course you can transform to whatever, right? So you want to have this matrix is a constant matrix multiplied by this x and y, you get the kind of like the output coordinate, yeah. So yeah. So okay. And then like, okay, but we still want to make it a matrix form. So what can we do? So we can wait. What we can do is like, let's say we have what we are going to do is like introduce something known as this homogeneous coordinate instead of the Euclidean coordinate. Okay, I cannot even spell coordinate. Coordinate. So what it does is very simple. It's like I have like x, y, and then put a one here to just append my vector here. So instead of like 2D, it becomes a 3D vector. And let's see if I think I copy somewhere here. Yeah. And this is hard to, okay. I just want to copy a figure here. Yeah. So it's an illustration here. just what does that mean? So I have basically another new coordinate. I have like let's say whatever x, y, and maybe I call it, yeah, it's okay. Like just according to this figure, x, y, and w here. You can think of like this point is more like in 3D now, and then like what you're interested in is like projected to this homogeneous plane. It's like for this w axis, like w is equal to 1. So, or you can think of like along this plane here. So for whatever coordinate, like that actual coordinate is like, let's say x pi, y pi. Actually, is this x pi, y pi is equal to x over w, and y pi is equal to y over w, something like that. So, or maybe I can say like this represent the same thing. So these two vector represent the same thing, same point in the image. So is that clear? I'm not very organized, I guess. Well, I mean, like, we have the coordinate. Yes, yes, yes. I guess I'm not very organized. So I have the coordinates. So originally Euclidean coordinates are just x, y, right? So what I'm going to do is I just append something. I say x, y, uh, um, x, y, 1 here. So okay, this one seems like it's dummy, but it's not, because I can vary this one also. I can put some different values. So what I mean is like if I have let's say uh scaling of this guy here, let's say I have s, x, y, 1 here, this will basically represent the same point on the image. So we will represent still the same point x and y. So for example, like this guy here, the original, let's say I have a point like 1, 2. Here, this is like the x1 coordinate, 1, 2 here. So I will have a homogeneous coordinate. Maybe let me write it here a bit more. Let's say my original point is 1, 2 here. This is the Euclidean coordinate. I'm not going to spell that. Okay, let me try to spell that. Euclidean, even though my spelling is wrong. And then like to homogeneous coordinate, homogeneous will be like 1, 2, 1, something like that. And as I said, like this looks like a dummy, but the point is like I can have like 2, 4, 2 also represent the same point here, and 3, 6, 3 also represent the same point here. So why do we want to do that? Because if we do something like that, then we can put also translation into the matrix form. Basically, I can have like x, y, let's say translate to like x plus let's say tx and y plus ty, and this is my x pi and y pi here. I can write into a matrix form something like x pi y pi 1 is equal to x, sorry, not x, 1, 1, 1, let's say x, y, sorry, yeah, x, y, 1 here. Let's see, what should I put in? I should put in tx and ty here, right? Is that right? No, actually it's not right. It's here, sorry, tx, ty, yes. So as you can see, like if I put a matrix like this, so I will have x pi is equal to 1 times x, basically x, plus tx, right? Tx times 1. So therefore x pi will be just equal to x plus tx. And similarly, y pi will be just equal to y plus ty. And 1 will be just equal to 1 here. Okay, so that's exactly what we get. It's like x pi, y pi is actually equal to a shift of coordinate by tx and ty. Now, and this is for translation, right? For translation. Now, if for scaling and so on, it would be like exactly the same as before. Like for example, if I have like rotation, that's rotation by theta. Originally, I have x pi, y pi is equal to like cosine theta, sine theta, sine theta. Okay, I forgot. Like, maybe it's here, right? I always forgot where's the minus sign is. Okay. So um, then if I use the homogeneous coordinate, my transform instead would be like cosine theta minus sine theta and sine theta cosine theta. Okay, I guess maybe I should let you to fill in. Maybe I would just say this is zero. What's the last row here? So I will have rotation in the original Euclidean coordinate. I will be like x and y multiplied by this matrix like that. Oh, yes. And then in the homogeneous coordinate, I have this guy will be, yes, multiplied by this one. Yes, actually, yeah, you guys get that. So, okay, similarly, I can do scaling, I can do translation. Now, everything will be put into this matrix form. If I use a homogeneous coordinate, then I see if I miss anything here. I can do I can put like basically uh uh maybe I don't have I'm not sure if I should show a slide or like I should put it down here. So okay, maybe I just quickly write it. So I will have something like so far we have see that is like I have translation. We'll have a form like that. The matrix tx ty sorry one here. This is one translation and for rotation, I just write above here is like cosine theta, sine theta, sine theta, cosine theta. Sorry, like for my shorthand here, I'm 0, 0, 1 here, right? I might have like scaling. Scaling would be like similar, right? Scaling have like S1, S6, SY, and 1, basically, something like that. This row here is all 1 here, or 0 here. And actually, you can do shearing as well. Shearing will be um, something like you kind of what should I say? I don't know how to explain that, but if you start from like this and move to this direction, it will be like shearing, right? So and we'll have a form. Okay, I'm not sure I remember the form. I guess it's like maybe I'm incorrect. Probably I say some S like SY. Yeah, I could be wrong, but don't worry about that. So and but my point here is like you see like I have matrix like all like that. The last row is like 0, 0, 1. And if I have like apply this kind of like transform, I have like first transform, transform 1, transform 2, transform 3, transform 4 to some coordinates here, homogeneous coordinate here, x, y, 1 here. Know that like when I do this transform multiplication, if my last row is 0, 0, 1, I will always also get back like 0, 0, 1 here because I have let's say uh, this multiplied by this guy here. As I said, like one way to visualize that will be equal to uh, let's see this guy wait, how do I read that? Oh yeah, I can visualize that as this multiplied by uh, uh, okay, maybe I just look at this row here is okay, right? This row here, if like I have these two matrices multiply together. So what's the last row here? The last row will be, oh, okay. I guess I shouldn't waste time like this, because you can easily verify, right? Then I guess you may go back home, or like you can easily verify that, like, but you can see that, like, if I have like matrices that the last row is like 0, 0, 1, you can do it easily, that like to see that this last row will be 0, 0, 1 as well. Because like the last row here, the first element here will be just like equal to this multiplied by this one here, right? So that would be 0. Actually, yeah, actually it's just like 1 minute. Actually, maybe I should still do it. So, and this element here, so it will be like this row multiplied by this column here, right? So again, it will be equal to 0, right? Because like this first two element is 0 here, so, and so therefore will be 0 plus 0, and then will be the 1 time plus 1 times 0 is also 0, and then the last one here will be like this one multiplied by this column, so that will be 1 here. So you see that, like, for all kind of this transform, when I multiply together, I will get the same form, will be something like 0, 0, 1 here, and I will have some values here. And all this is known as the affine transform. So in general, therefore, like if I have a matrix like that have some values here, and I have 0, 0, 1 here, this transform here will be known as a affine transform. And I don't have time to show that, but like you can try to show that yourself, or like if you are considering a affine transform, any parallel line that start with like in the original image that is parallel, after the transform will be parallel as well. So what you can show, okay, the way you can show that is like you can think of coordinate, let's say, let's say this original point is x0. So here I just make it a vector here. And this point here is, let's say x1 here. Now this line I can be parameterized as a x0 plus t, let's say tx, t dx, maybe I call it dx, t dx. And then this is a x1 plus t dx. Then if you apply this transform, affine transform, I'm assuming this one is 0, 0, 1 here. So you should get also something like x, let's say x tilde 1 and x tilde 0, and parameterized by something t here. Of course, my direction will be different. I have t dx here, dx tilde, let's say, plus t dx tilde here. So what I mean is that in general, these two can be different, right? The direction of moving can be different, but you can show very easily that like these two will be the same. So therefore, like the line will still remain parallel. So now, okay, let me give a question here again. So is this, if I want to do this thing here, I have this image here. I want to warp to this shape here so that I can do like image stitching. So is this a affine transform? So is the question here from our discussion just now, affine transform, for affine transform, any lines in the original image are parallel, okay, or any parallel lines in the original. Okay, affine transform is like this. Have the form like a B C D E F 1, something like that. So that includes scaling. You see, right? Scaling, translation, and the rotation, and shearing, yeah, so on. So because you see like all yeah, all of this is this form, right? So and in general, this form is known as affine transform. Right? So okay, good, good, good. So but why is not? Why is no? So because we just mentioned that. Oh, yeah, actually, I have prepared the proof here, but I'm not going to go through that. So that if you have parallel line, actually maybe I can quickly see that if you have parallel line here, let's say I have one line here, say x0, y0, 1 plus tx pi. So this will be represented line, right? So if I multiply that, I will get for a affine transform, I will get something like this, right? So, and basically will be, if like for parallel line, this part is not going to change with my x pi, y pi is the same thing. And but the point of starting point can be different. So I can have this x0, y0, 1 will be different. So this one will be different. But this guy, as you see, only depend on the direction of motion. So it's like this depend on this x pi, y pi is where I'm pointing the direction here. This direction is not going to change. So therefore, like if I start with like this point and I'm construct a line, and I start with this point, construct a line, and I transform that will have a new point like for correspond to another point like and correspond to another point, this one to another point, this one to another point, and but the direction of moving here, this basically this is the direction will be basically the same, so same direction. So it will be okay. Yeah, I sorry, like it's a bit tempting since I already draw it here, but it's okay. I know that if I speak like that, it's very hard to follow, but I'm just want to say that if you want to show that, it's very easy to show. So, but so for affine transform, yeah, everything parallel will be parallel, right? And this apparently is not, right? So I have this line here, these two lines are originally parallel, right? And like I map to something like this. So therefore, like it's not a affine transform. So this is something else, something beyond that. So what we have here is like so long as this homography, or like projective transform, or like perspective transform, or something like that. There's many names for that. So basically, the transform will be very similar, but I have these guys here can be non-zero as well. So I can have like A, B, C, D, E, F, G, H here. So this will be a homography. So then I can have like transform like this basically. So I guess at this point I can just quickly go through some of the slides here. That's just basically just repeating what I said so far. So wait a second. I need to see your chat again. So here is like what we talked about at the beginning, right? So if you think of filtering and warping, the difference is like filtering, you're applying the transform or like whatever the function to the intensity of your image. So for example, you have this one, you can shift that like up and down and so on, right? But if you're doing warping, you're actually applying the transform to the coordinates that. So then you maybe kind of like here is a stretching. This is just showing 1D, so it's a stretching in 1D direction. And so this is another example in 2D. So image, like if you filter, it will be like this, right? So every pixel is still, you can think of synchronized to the original, right? So original location pixel is here, the corresponding pixel is still here. But if you're doing warping, like that basically is the coordinate that change, right? And so we have translation, rotation, I am scaling, aspirate. So okay, like this is just repeating what we said earlier. Um, so yeah, scaling have this, right? And then have this is rotation. Now, and this is okay. I'll go really quickly. That so translation. If I use Euclidean coordinate, I cannot put in matrix form, right? So that's why it motivated us to do a homogeneous coordinate. So we introduced homogeneous coordinate, and so with homogeneous coordinate, then everything can be put into a matrix form. My translation is like this, and basically also like this will be then therefore like in general, if I have like this row here is 001 will be a affine transform, and affine transform is closed in the sense like if you have multiple affine transform applying one at a time, the resulting transform is still affine. So we have like this several of example like of affine transform, right? And then the one thing like we mentioned, right, affine transform, if lines are parallel, it will remain parallel. So therefore, this will not be a affine transform, right? So then therefore we elaborate, kind of like extend that, like we'll get to uh, generalize that into the homography that I have these two coefficients can be non-zero as well. Then this I can get something like this. This is a homography. Like I have kind of like different, very interesting new perspective basically. So this is a very interesting example where you can see that like I have the original image. You say that I have a view like this. I can get like a view like seen from the top, like using perspective transform. As long as you know what's that transform here. So that will lead to some other time we will talk about that after we talk about like features. uh Basically it's like quite easy, right? So as long as you know where's the point, like here for example this point, let's say this point correspond to this point here, and this point correspond to this point here, let's say, and this point correspond to this point here. I have multiple points of that. Then I will be just need to solve some equations like to find that transform, right? So I have unknown. Basically for the homography, I will have like 8 unknowns, right? Because I have a 3 by 3 matrix. I have one of that. The lower corner value is uh, basically I have this one is I specify I have 8 unknown here, right? And and okay, I guess I may I yeah, and this is another illustration also. I can also look at like another kind of from another perspective. Of course, here it looks I have to I mean blur here because I don't actually have information here, right? So I think like this is like from what view? Yeah, it's for this point for this like pixels here. So I don't have much information here. So I kind of just interpolation. Therefore, it's a little bit blur, but you see the point basically. So let's see. So what else? Okay, this is a just a summary slide basically. So I have translation would kind of like similarity transform and then okay, let's see. Translation is like that. So I have a Euclidean that basically just rotation plus translation. So just say I have move the objects like rigid object, move it around, and I can have like similarity transform. I can uh, rotate, translate, and also like scale it, and I can do a affine. So here also like specify how many coefficients there in the sense would be like the degree of freedom, right? And finally I will have like projective transform and say have like the the most number of parameters is also like most feasible. Um, I actually yeah I spent a bit more time than I thought here. Uh, Maybe I ended uh with just another quick demo. Not on that one. Maybe like just in case you guys have maybe like next time I will come back to show a little bit more demo and open series stuff maybe. But here like okay I really want it out. But let me just for let's see if I can, because I think like you guys should start working on the homework assignment because don't wait until the last minute. And I want to find my, oops. I cannot, you don't know what I'm doing, but I'm basically looking for my code here. Oops. Because it's the homework solution, I cannot show you. So, but scaling. Oops, why I don't have that? So okay, anyway, I guess I will show you next time then. So that yes. So I okay. Anyway, I really over time now. So I guess I'll stop here really. So if you guys have any questions, I guess I will wait for a sec. Otherwise, I will just end the meeting here.
Professor Chang,
Yes.
so could you upload an image file that is dave.jpg? I like to reproduce this code. So I just want to rerun your code in the website, but I don't have the image file.
Oh, okay, okay. Let's see. Let me just take a quick look here. So, which one is that?
It's edge detection.
Oh, okay.
So
Let's see. Oh,
I
no,
wanted to
actually, the
use the
other one got it.
OpenCV edge detection. Yes. So in this note, we need image file dave.jpg.
Oh, yes. Okay. Let me put it somewhere so that or maybe I will update this link here so that you can, yeah.
Okay, thank you.
Okay. Yeah. So, okay. So if no more question, I will see you guys on Thursday then.
I actually have a question.
Okay. Yes.
So this is a homework question.
Yes.
I have so far gotten a low pass filtered image
Yes.
from an image. When I tried to do the high pass, I'm getting some weird noise, and I'm not sure why. All I did was I took the original image and subtracted the low pass, but it doesn't look quite right. Can I share my screen or something?
Oh, yes. Wait a sec. Let me. Yes, you can.
Okay. Gotta find the right one. Hold on. So, yeah, this is what the image looks like when I filter it through the high pass, and I'm not sure why. I don't know if that's correct or not.
Actually, it's kind of correct. Like, yeah, the noise is like you cannot avoid that. So because yes, this is actually the noise here is you have this is JPEG image, right? I guess
Yeah.
it's like the image itself, like when they are compression, like typically the edges, like they have this blocking effect and so on. Like when you just if you don't go through the high pass filter, typically you don't see that like quite easy. But because you have the high pass filter, like you filter out the low pass thing, like now become like quite apparent. So yeah, that's actually is okay.
Okay.
So as long as for the homework. So but
Okay.
yeah, yes, I actually like maybe next time I will show you like what I have. Like I do not manage to get something really good also, but it's you can still see the effect here. I guess yeah, I will show you guys next time like what I have. Yeah.
Okay. Thank you.
Yes.
Right.
So any other questions? So if not, I will see you guys next week then. Or not next week, I'm sorry, like Thursday then. I'm really yeah.